Hello, everyone. Now I'm going to introduce our work about a dynamic dispatching method in the amended airport baggage transportation system. I will introduce it from 5 aspects. First of all, it's an introduction of the whole work. As an important component of the airport ground transportation system, the operation of the baggage transportation system affects the efficiency, safety, and cost expenditure of the whole transportation system. However, there are some problems with the existing method of baggage transportation. First, metro baggage transportation vehicle development method cannot respond to the demand of large-scale flight baggage distribution in a timely and efficient manner. Then, the traditional way of single vehicle service for single flight is usually adopted. For the vehicle serving the baggage transportation task of outboard flight, it will return to baggage sorting area empty after completing the loading of passenger checked baggage transportation. The traditional scheduling method will cause the service not to be timely in the case of surging traffic. The last, when there are changes in flight service demand caused by late flights and flight delays, the metro development method is difficult to develop an optimal travel plan in a short time due to the limited ability and experience of decision makers, and is prone to problems such as untimely response, increased transportation costs, and wasted transportation resources. So, how to further optimize vehicle routing and the dynamic damage response of amended intelligent baggage transport vehicle in Sylvie Richardson Airport. It's in its real option scenarios so as to optimize airport service, reduce energy consumption, and reduce cost is a challenge we face now. In this work, we have 3 main contributions. First is construct a recurrent natural network to predict vehicle dynamic driving conditions and establish a vehicle dynamic demand response model. Second is propose an improved genetic algorithm to solve baggage transport vehicles routing problem in static phase. Third is propose a dynamic vehicles path update algorithm to solve baggage transport vehicles path update problems in dynamic phase. The second part is problem descriptions. To describe the problem of baggage transportation in airports precisely, we abstracted the real airport baggage transportation scenarios into a directed graph and built a model of airport baggage transportation system. The symbols and their corresponding meanings has been displayed. As one of the most important components of baggage transportation, the carrier vehicles also have been abstracted into a model with mathematical symbols and equations. The model also has been displayed. And we construct the constraints and objective functions of baggage transportation problems by using the parameters in the above model had mentioned in final. Part 3 is dynamic dispatching algorithm for electric baggage transportation vehicles. To solve the static phase vehicle path problem, we propose a genetic algorithm as shown here. And to achieve real-time update of text nodes and the dynamic service response of vehicles, the concepts of timeline and critical point introduced in this work. Then we constructed a recurrent neural network based on the attention mechanics to realize the dynamic prediction of the critical points of the vehicle. The network structure is shown in the figure. The network inputs as a vehicle scheduling task sequence, the real-time vehicles group location map, and the real-time weather information. The maximum probability task point is obtained by softmax function as the output of this network, which are critical points of vehicles routing. The critical points prediction algorithm is shown on the right. As shown, the dynamic demand node service cost consists of three main components: the task cost, time opportunity cost, and time impact cost on each subsequent task node. And based on the model of vehicle dynamic demand response, the dynamic phase vehicle path update algorithm has been proposed, which is shown here. Part 4 is simulation and experiment result. In this part, we give an example to do the simulation. For the simulation as close to the real thing as possible, here are some settings of our example. We stipulate the airport total has 64 parking spaces with 1 vehicle parking area and 12 baggage handling areas, which includes 6 baggage dispatcher areas and 6 baggage arrival areas. Baggage departure areas 1, 2, 3, 7, 8, 9 points, and the baggage arrival areas 4, 5, 6, 10, 11, 12 points. And the rest represent the airport parking areas. In addition, the vehicle's speed and the rate, maximum load, and the deadline weight of the vehicles also has been set. We also set 5 dynamic changes of flight information in a single day, and 2 new flights will be added into the port. The change of flight schedule will be designed randomly among the flights not yet served at the time of the change. The specific change and data will be generated randomly, and the earliest service time after the change cannot be earlier than the current time. During the dynamic model experiment, the new task nodes are inserted into the original distribution path using a dynamic solution insertion algorithm for the problem model based on the new randomly generated flight information. The result of 2-phase simulation have been shown in the figures. The final part is the conclusion. In this paper, we constructed a static distribution path model for amended airport baggage transportation as the airport baggage transportation system. We also designed a genetic algorithm and dynamic vehicle path update algorithm. The dynamic change of flight information are considered in our algorithm with the prediction the critical points in the past. Finally, based on the configuration of the actual airport and real data, we conduct simulations to evaluate our algorithm. That's all my speech. Thanks for your watching.